Okay, this screencast is about the log laws, and there are a few of them. Pretty straightforward, and they really help with calculations and things like that. So let's get straight into it. We've got just to recap that the log of 25 to base 5 is equal to 2. So we've just to get the directional aspect right, 5 to the power of 2 equals 25. That's the sort of direction it goes in. 5 to the power of 2 equals, that's kind of the way it moves around. That's what an anti-clockwise sort of direction, starting with the base there. All right, so that's what logs are. So let's have a look at log law 1. Okay, log law 1, you're going to love these. Log law 1 is that the log, all right, now I'm not going to write a base here because it doesn't matter. The base is consistent through. So log of xy is equal to log x plus log y. Now there's a nice little proof for this. It's not hard. I'm not going to go through it on this screencast, but I might put another one together just with the proof. I don't know, but it is related to the fact that we know that with when you multiply terms together with the same base, you add the powers, and because logs are to do with powers and indices, that's why this multiplication of xy turns into an addition. And you'll also see that the log law 2 works the same sort of way with division. So log of x over y, or divided by y, will equal log x, you guessed it, minus log y, division working to subtract the powers with common bases. All right, a little example here. If we say log, let's say, remember, if I don't write a base, it's base 10. So let's just go with base 10, log 25 plus log 4. Well, we can work this way on log law 1 to deduce that that's equal to log of 100, and log of 100 is equal to 2 because 10 squared is 100. If we look at an example here, let's look at log 50 over 5, for instance. Oh no, sorry. That's just log. That's it. That's too simple. Log 50 minus log 5 is what I meant to write. Then we use this law, log law 2, to say, well, that's equal to log 50 over 5, and that's just log 10, and that's just equal to 1. Okay, just a couple of straightforward examples just to see how that works. Now, log law 3 is probably my favorite log law, if not mathematical law, and it is because I love the use of it. It's log, let's have a look at this. If we've got log base a of x to the power of p. Okay, so we're logging x to the power of p base a. All right, this is a beautiful thing. This p comes down the front here, and this becomes plog a x to the power of a, sorry, x to base a, and it has become known as, in my classes anyway, as the plog law. The plog law. All right, and you're going to enjoy saying that word. So anytime we talk about plogging, what we're doing is talking about taking a power and bringing it down the front. Now this has huge power, huge use for us in solving equations. So if we want to solve, let's say we want to solve 3 to the power of x is equal to 10. This is a beautiful thing. We can say, all right, I'm going to take a log of both sides. So it's log 3 to the power of x equals log 10. And well, that's going to be, I'm going to use plog law now to bring that x down. So it's x log 3 is equal to log 10. How good is that? So that power of x, which has been troubling us, now using the plog law, down it comes, and log 3 is just numerical value. So x is now equal to log 10 over log 3, and that's equal to log 10 divided by log 3. Well, log 10 is just 1, so I'm just going to put in, where's my log button here? Control, is that it there? Log, go straight across to log 10. Now what am I doing? Dividing by log I'm going to still base 10, so I just whack a 3 in there, log 10 divided by log 3, hit enter. I need to get the 2.09 or 2.10, 2.10, so 3 to the power of, we knew it was a bit more than 2.10. So that's how logs now are going to help us find solutions to equations using the log law 3. Now I just got another little use of the plug law. If we have log, so using the plug law, we can say that log base a of 1 over x, we can write this using our negative index knowledge to write that as x to the minus 1, and then we can use plog to go, well, that's minus 1 times, or just minus log a to the x. So in fact, log base a 1 over x is minus log base ax, which is a nice little result. We'll use that a little bit. There's one more log law 4. It's the change. So log law 4 is the change of base theorem. Change of base theorem. And it says that, right, if I've got log, and maybe I've got it to base a, and I've got log x to base a, and I don't fancy this base a business. And there's plenty of times when we want to change the base. Now it might just be we want to change the base to 10, so we can use our calculator and base 10, or it might be that we want to get them in the same base so that we can work some things. We might want to get to a natural base, log base e, which when we get into calculus and using logarithms in calculus, which sounds crazy hard, but actually when you get into it, it's not too bad. But we have times when we want to change this to base e, so we can do some calculus. So this is a really useful theorem as well, and it's simply this: I can change this. I can change to whatever base I like. Let's go to base b, and it's just x over log base b a. So you see what's happened there? I just changed the base to b, becomes a fraction, and I've got x over a in those positions. That's my change of base theorem. Let's do a few examples, and then we'll be right to go into the exercises. So, okay, this example here, so examples of using the log laws. Let's have a look how we can use the log laws to simplify this into maybe just a single logarithmic expression. All right, so log 5, there's not much we can do with that at the moment, but this half, I can unplug this. And if you talk about going up this way and putting it back in, because I think that if I put this in up here, 36 I know is a square number, and that half, if I put it up there, is 36 to the half. Well, I can write this therefore as 36 to the half, right, that there, and then I can get this log 10 in there. Now this 36 to the half is just 6, isn't it? So I've now got log base 2 5 plus log base 2 6 minus log base 2 10. All right, now this plus, log law 1 says that I can combine that plus, doesn't it, into a 30, and now I'm going to combine the minus into a log base 2 30 over 10. So I end up with, finally, log base 2 3 as my simplified answer. Isn't that fun? I told you it'd be good. Okay, next example. I'll write up in a sec. Okay, and this example looks like crazy, but we've been given A's, B's, and C's in terms of what they represent, and we've got this here. Now, what we're going to have to do is get this, sort of use the log laws to unravel this and pull it all back and try and get it in terms of just log x's, log y's, and log z's. And then we can write it in terms of A, B, C. So let's get to work. What's this division? Let's go back up here and see what the division was. It was log law 2, and right, so log x minus log y. So I can write this here, I can write that as log 5 square root x, but I'll write that as x to the half, right? Minus log base 5 y squared z cubed. Okay, so I'm sort of unraveling it a little bit here. Now this here is, I can plug this, so I can get a half log 5, sorry, not log 5, but log 5, log base 5x, right? So that's down there, that's looking good, and I know now I've got, that's a half a, so I'm in business there. Now this one here, I've got y squared z cubes. I really need to split them up. Now, this is like my xy, isn't it? So I know that I can go, right, well, that's log 5y squared, is it plus log, using log law 1, z cubed? All right, is that right? Now I've got to bracket all that because I'm subtracting that whole thing. All right, so now I've got a half log 5x. Now this 2 I can bring down. I need it to come down because b's in terms of log y, and not y squared, so I can plug this. So I can go minus 2 log base 5y, and then this 3 can come down as well, but I'm subtracting 3 log 5z. So now I've got the whole thing worked out. It's a half a minus this log 5y is 2b, and log 5z is c, so it's minus 3c. A half a minus 2b minus 3c. Excellent. Maybe another example. Okay, our final example is on the screen. Given that log base 3x equals a and log base x6 is equal to b, write this in terms of a and b. Okay, now our base here is 3. I want to change it to x, so can we write this? Let's write this. That's log base 3, 6. We can write that as log 6 over log 3, and I can write whatever base I want here. Now, let's go with base x because that's what I've got for a and b, and log 6 is b, and log 3 base x is a, so we're done. Okay, we should be good now to go with for m, n, and o, I believe. So exercise for m, for n, and for o, which is Tuesday's work. And so I'll see you then.